I know I have, and I bet you have too. You've taken a shower or a bath, or you go swimming and you get out and your hands are all wrinkly, right? Is that because water that you were swimming in entered your hand, or was water leaving your hand and going into the lake or stream or swimming pool? Matter always travels from regions of high concentration to regions of low concentration. So if you are sitting there in a swimming pool, the water outside your body is a much higher concentration than the water inside your body. The reason being because inside your body, you've got all these dissolved solids, right? You've got blood and red blood cells, and you've got all these proteins and all these things inside your body, inside your aqueous body. And outside your body, it's a much higher water concentration. There aren't all those dissolved solids. For example, you can fix wilted lettuce by taking advantage of osmosis. So the lettuce is wilted because it's dried out. The water is entering the lettuce because it's more concentrated on the outside. So it travels from a region of high to low concentration. So the water travels back into the lettuce leaf. That's osmosis. Now, to understand what's coming up here, we need to have an idea of just how big a water molecule is. If you have a strand of hair, that's around 70 microns or so. Okay, it's around here somewhere, pretty much the same as sand particles. And if you get even smaller, go smaller, you can get bacteria and viruses and vitamins, sugar, salts. Okay, now you're getting down to where water is. Water is probably way over here somewhere. Like 0.0001 microns. 0.0001 times 10 to the negative 6 meters. So water's really small. Now why am I telling you that? Because we need to understand a few things here about osmosis. Here I have, in the top channel, I have roughly 50 particles. 40 of them are green and 10 of them are blue diamonds. On the bottom I have 50 particles again, but they're all green spheres. So my green spheres, whether they're the solvent, right? Because they're in the majority, whether I'm in the top or the bottom region. And these regions are separated by a membrane. So let's say the green spheres are water molecules, my solvent. Right? Is the solvent more concentrated in the upper region or below the membrane? It seems odd, but it's more concentrated where there aren't any solute molecules. Right? There's solute here taking up space. Down here there's no solute, so it's pure solvent. It can't get any more concentrated than this. So with osmosis, it's natural for matter to go from regions of high to low concentration. So if I put some little membrane, make this a semi-permeable membrane so that only the solvent can pass through. All right? So it's very, very tiny. Only water molecules can pass through. There's going to be a net movement of water molecules from the region of high to low concentration. Water is going to end up actually flowing to where there's dissolved solids. That is osmosis. In this animation, what would be reverse osmosis? Well, reverse osmosis, we know it's natural. Nature wants to go from this region that way. Reverse osmosis would be, okay, let's stop that natural movement. let's apply a pressure on this side. Maybe it could be a piston or something like that, and let's push back. Let's push back, and we'll see that not only will the osmosis stop, but it will reverse. Water will then travel from a region of low to high concentration. That's reverse osmosis. That's one way to get pure water out of ocean water, is reverse osmosis. Here's an example of osmosis. It's kind of a mean thing to do, but if you have a snail and you add some salt to that poor little critter, right, there will be the water inside the snail will be at a higher concentration than the water outside the snail because you added all this salt. Now it's all salt water. So the water is going to move from inside the snail to outside the snail. And you're just kind of desiccated and dehydrated. That's where all these bubbles are forming. Just what is osmotic?
A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
This beaker contains pure water. Inside this ampule is sugar water, and this is a semi-permeable membrane. So as the ampule is immersed into the pure water, water will travel through the semi-permeable membrane and into the sugar solution. High concentration to low concentration. So as the water travels through the semi-permeable membrane, the level, the height of the solution keeps getting higher. And as the height keeps getting higher, well, that means the pressure on the semi-permeable membrane, right, is going to get higher because there's more and more solution, more height, more and more weight. So as that weight keeps increasing as the height keeps increasing. So, but sooner or later, it's going to stop because the rate of water traveling through the semi-permeable membrane is going to be the same in both directions. So, and when it stops, whatever that pressure is being exerted on that semi-permeable membrane, they call that the osmotic pressure once we reach some equilibrium height. So we have an equation for osmotic pressure. And let's take a look at what the units could be for all of these things. I think we should start with R, though. R will, you remember R? The gas constant. 0.0821 liters atmospheres over a mole Kelvin. That was the units for R. So that means T should be Kelvin. I'm going to use this equation. Kelvin. Here's our osmotic pressure, pi. It should be in atmospheres. So that leaves big M. What's left? All what's left are the moles and the liters. So remember moles per liter? Molarity. Big M. So that's our equation for osmotic pressure. The molarity times the gas constant times the temperature in Kelvin. That's how you can calculate osmotic pressure. So now we've got, you remember these vapor pressure lowering, boiling point elevation, and freezing point depression equations? Well, now we've got one more for osmotic pressure. And so that's what we had before. Now we've got a new column, though. The equations are very similar. It's just that we had ionic solutes now. So before we had molecular solutes, like the solutes, no ions can be present. For example, sugar. Now we can have ionic solutes. So depending on whether you have a molecular solute or an ionic solute, you're going to use a different set of equations. And notice the only difference is this little I. There's no I over here. So how do you get this little I? Let's play with these a few. The little I is just the number of ions. The number of ions that that solute will break up into. So for example, let's say the solute was potassium sulfate. How many ions does potassium sulfate break up into? Well, it would break up into 2 potassium ions and a sulfate anion. Well, that's 3 ions total. So that's what I would be. I would be 3. Potassium bromide, I would be 2. Because I have a potassium ion and a bromide anion. How about sodium phosphate? I would be what? 3 sodium ions and a phosphate? 4. What if the solute is carbon dioxide? What would little I be? Well, it does 0, right? It doesn't apply because it's not a ionic compound. That's a molecular compound. So if your solute is carbon dioxide, you're going to be using this set of equations, that column, because it's a molecular solute. Here I have 2 containers of water. This one is pure water, and this one has a very small amount of coffee creamer in it. And coffee creamer is just big globules of fat, pretty much. And they both solutions look the same. However, this is a colloidal solution, a colloidal suspension. How can we tell? Well, we can tell by the Tyndall effect. If I shut off the light and shine a laser through the water, you can't see the laser being scattered. However, when I shine the laser through the colloidal solution, those big fat globules, those colloids, will scatter the light and we'll see the laser. That is the Tyndall effect. So let's go ahead and work a few problems. An aqueous solution contains 0.296 grams of a polymeric molecular unknown. If there is 125 mils of solution, the temperature is 25, and an osmotic pressure of 2.58 millimeters of mercury, what is the molecular weight of the unknown? Okay, so you can tell this is going to be an osmotic pressure problem. So we have 2 choices. Which one is it, right? Okay. So you may not see how to exactly solve for molecular weight yet, but this is how we're going to have to start. We won't use this one because it's not an ionic compound. They didn't tell us a salt so we can figure out the number of ions. It has to be this one. Okay. So what's the game plan? The game plan, I think, is molecular weight is always just the number of grams all over the number of moles. So they already told us half the answer. Do you realize it? They want us to find the molecular weight of the unknown. Well, the grams of the unknown, they told us. And we'll just have to calculate the moles of the unknown. Right? 0.296 grams, the grams of the unknown. We're halfway there. So we are going to use this equation, the osmotic pressure equation, to find the number of moles. And then we'll plug it in down here, and we'll have our molar mass of the polymer. So let's go ahead and get started. Pi equals MRT. See how we can get this to work. Osmotic pressure equals MRT. Well, the osmotic pressure, they said, was 2.58 millimeters of mercury. But remember that osmotic pressure has to be in atmospheres. So let's convert it into atmospheres. And I give you all these conversions on the quiz. There's 760 millimeters of mercury in an atmosphere. So 2.58 divided by 760, you get about 3.39 times 10 to the negative 3. Okay, so let's go ahead and plug that in. We've got 3.39 times 10 to the negative 3 atmospheres equals big M. We don't know what that's going to be. R is 0.0821 liter atmosphere over moles Kelvin. And the T they said was 25 degrees Celsius. Now remember, to get Kelvin, just add 273. So that's 298 Kelvin. Okay, so do you see why we are solving for molarity, big M? Because it has moles in it, right? Because big M is moles over liters, so we'll be able to solve for it. Let's just get big M first. So 3.39 times 10 to the negative 3 divided by, that should be 0.0821, right? Divided by 0.0821 divided by 298, you get about 1.39 times 10 to the negative 4 molar. So now I can just set up my big M equation. Remember, big M, moles over liters. We know that big M is 1.39 times 10 to the negative 4. That has to equal moles. And the liters, they said, was 125 milliliters. Well, 125 milliliters is 0.125 liters. So let's solve for moles. Pretty much just going to bring the 0.125 liters up to the top with the 1.39 times 10 to the negative 4. So we multiply them. About 1.73 times 10 to the negative 5. Okay, so let's plug that in for moles. So my molecular weight is going to be, what did we say the grams was? 0.296 divided by 1.73 times 10 to the negative 5 moles. And I will get my grams per mole. About, what is that? 17,066 or so. Right around 17,000 grams per mole. It's a huge molar mass because it is a polymer. They said it was polymeric. So you're always going to get huge numbers for polymers. Okay. It's just, in nature, a polymer is just a compound that's just the same thing repeating over and over and over again. They are huge, huge molecules. In a mountainous location, the boiling point of pure water is found to be 95 degrees Celsius. How many grams of sodium chloride must be added to 1 kilogram of water to bring the boiling point back to 100 degrees Celsius? So do you recognize this type of problem? A boiling point elevation problem, right? So here we are. It's going to be one of these two. And which one is it? It's going to be this one because the solute is salt, right? We have ions. So delta TB equals I KBCm. So the boiling point elevation equals I times the abelioscopic constant times the molality. Okay? Okay. So how many grams of sodium chloride must be added? Okay. So this is going to be another two-part problem, right? Because first we're going to find Cm, right, using this equation. Second, we'll use molality to get grams of sodium chloride, right? Because molality is the moles of solute or the kilograms of solvent. Moles of sodium chloride over kilograms of water. So we can solve for moles of sodium chloride and convert into grams of sodium chloride. So let's do the first part first. Let's find molality. This boiling point elevation is how much the boiling point changed by. Well, it changed from 100 degrees Celsius, 95, so it'll just be 5. My little I have sodium chloride. So that means my I has to be 2. I have 2 ions. The boolioscopic constant is 0.512, and I'll solve for my molality. So 5 divided by 2 divided by 0.512, about 4.88 molal. Okay, so my 4.88 has to equal the moles of sodium chloride divided by the kilograms of water. It's just 1 kilogram, right? It's just 1 kilogram. So my moles of sodium chloride is 4.88. Okay, so I guess we have a third step. We have to convert to grams. We'll have 4.88 moles of sodium chloride. Okay, periodic table. Chlorine is 35.45. Sodium is about 23. So 35.45 plus 23, about 58.5. Looks like it's around 285 grams of salt. Okay. So in this problem, it was a boiling point elevation problem, and we picked this one because our solute was a salt. So the first thing we did is we solved for the molality. Okay. Then we used our molality equation to solve for the moles of our solute, and then we converted our moles of solute into grams of solute. Calcium nitrate is dissolved in 100 grams of water. The solution freezes at a negative 0.085 degrees Celsius. How many grams of calcium nitrate were dissolved to make this solution? So this is going to be a freezing point depression problem, right? And it has ions, so we better pick the expression with the I. Okay? And they are after grams of calcium nitrate. So do you recognize the problem? See a game plan? We'll use this to get CM. So first, to get molality. Second, we'll use molality to get grams. Okay, so try it. My delta TF is just going to be the amount that the freezing point changed by, and it is changed by 0.085 degrees Celsius is all. I is my number of ions, and I have calcium nitrate, so if this broke up, I would get 1 calcium ion and 2 nitrates. So that's 3 ions total. My constant is 1.86, so I can solve for CM. 0.085 divide by 3 divide by 1.86, get about 0.015. 2 or so. Okay, so let's plug that in up here. My molality equation, moles of solute, which is calcium nitrate, divided by kilograms of solvent, and the solvent is water. So my molality is 0.0152 moles of calcium nitrate dissolved by how many kilograms of water? I've got 100 grams, so that's 0.1 kilograms. So what's my moles of calcium nitrate? 0.0152 divided by 0.1 is 0.152 moles. So there's only one step left. We need to convert 0.152 moles of calcium nitrate into grams. And then I will have my answer. Okay? So let's find the molar mass of calcium nitrate. Calcium is 40.078 plus 2 nitrogens, 2 times 14.01 plus 6 oxygens, 6 times 16, get about 164.1 times 0.152, about 24.9 grams of calcium nitrate. So with these problems, I give you all these equations, and we just have to know how to use them. A lot of them are multiple, two-step problems, but give them some practice and come by if you have some questions.